So big abbreviations come out of OChem. Every point is defined to be a carbon. Okay, so don't lose track of carbons. And don't unintentionally draw a line thinking that, well, that's the end of the structure, and you've now added an extra carbon. Okay. So you have to be careful with how you draw structures in and make sure that you aren't accidentally implying an extra carbon. Hydrogens are very often, if almost always, implied to carbon, okay, to satisfy an octet. So that again, if we drew out a line, we'll draw out a couple examples because they're relevant for the homework. Okay, if we drew this, okay, hydrogens are implied to carbon. So what are the implied hydrogens in this structure?
Hydrogen off of carbon.
Hydrogen off of what carbon?
The one on the right.
The one on the right has a hydrogen attached to it. Are there any other implied hydrogens? Yeah, where else? The leftmost carbon, that's a point, isn't specified as a carbon, but by definition is a carbon. And you're correct, you're saying there's how many? 3 implied hydrogens out there. Okay. So let's take a quick moment here. You will easily forget this, but when it comes to smart work, what we just said was all of those hydrogens are implied. We didn't necessarily have to specify them. However, if you were asked to draw this structure in smart work and this is what you drew, you'd be marked wrong. Okay. At least one of you knows why, because you sent me an email complaining about the question. Who's that one person? I don't remember who it was. Who? You? Okay. What's the issue?
Well, I put it in like that, and I kept clicking, what is it called, check answer, and it's wrong.
Yeah.
And
So.
then when I clicked view solution, it was that answer.
I thought there was something else, but I could be wrong. If you see the letter C in smart work, you must specify all bonds, period. Okay? So as this is drawn with that C, if you enter this into smart work, what does smart work think? That you have a carbon missing its octet. Is that a valid structure? No, so it freaks out and complains. So if you see the letter C, make sure you don't imply hydrogens, that it's attached. Okay? The next thing. Let's say in running this reaction, this was a horrible statement to make, but we're going to do it anyway. Because at this point, I don't think you guys know any better, so it's okay. We run a reaction where we added these 2 hydrogens, the purple hydrogens. So we started with something, and we made this. What you are accenting is that you put those hydrogens on, that those are new hydrogens. Okay? Officially, do we need to specify the hydrogen on the left? No. Even if you've added it during the process of the reaction, we don't have to specify it because hydrogens can be implied. I don't have to show it. I could just erase it. So what you were doing is showing that both those hydrogens were added to the structure, that they were new hydrogens, and you're now trying to be fancy by showing that. Which then brings in the next issue. According to how smart work grades, you are then saying, or starting to show that hydrogens are not implied by showing that hydrogen. You've now removed the implication. Which means smart work looks at that structure and at that leftmost carbon, and it says there's only 2 bonds, you're missing an octet, your structure's wrong. Okay. You either specify all bonds or imply all bonds. There's no in between. So as soon as we've drawn on that 1 hydrogen, we must show the others. Or we get rid of them altogether.
So you just have to put in the 1 hydrogen with the carbon.
The 1 hydrogen with the carbon, that one you would always have to specify because you see the C.
How come it can't have a lone pair?
Smart work will definitely not assume a lone pair on that carbon. Yeah. And then the lone pairs being implied on the later ones moves into our later rules, and we'll kind of get into that. Okay. So it's kind of a smart work issue. So when it comes to entering, which makes me nervous because you said you drew it, and then you clicked check answer and it said it was wrong, and then you click check answer again.
Well, I changed it to
Okay, now I'll accept that. Okay. There's no check answer, it's wrong, change it, check answer, it's wrong, change it, check answer, it's wrong, change it, check answer, it's wrong, change it. You did that too many times. 3 times. 1, wrong, 2, wrong, 3, wrong, email. Okay? That's how it works. Right? Don't start getting locked into a cycle of fighting programming. You will lose. Okay? So our hydrogens are very often implied to carbons to satisfy octets. On pen and paper, everything we just discussed here would be graded as correct. Okay? Even if you drew on that one hydrogen, you'd be hard-pressed to find a grader that would then go through and say, well, that's wrong because you can't imply one hydrogen and not the others. Okay? So it's a programming issue within online systems. Our next rule is charges are never implied. Okay? We can only imply one thing, hydrogen. Okay? So you can never, ever, ever assume that an atom is charged. Okay? So if we drew out this structure. Let's fix that. Sorry. Let's try that again. Okay. This structure. Okay, we've got implied hydrogens on that leftmost carbon that wasn't specified. Okay, so we officially have a CH3, so that's okay. We have a full octet on that carbon, and then we run into an issue with the oxygen. What's that issue with the oxygen? All sorts of things are popping up in there. It's actually not negatively charged. It's missing a lone pair, okay, which is kind of our rule 4. Very often, nitrogen, oxygen, and your halogens will have implied non-bonding electrons to satisfy octets. So if we looked at that oxygen, it only has 3 bonds, which means there's an implied lone pair, which is exceedingly irritating, but there's 1 to satisfy that octet. But then what's the next issue? That oxygen is charged, it's a +1. You can never, ever, ever imply a charge. And that largely goes back to bullet 2, that hydrogens are implied. We can only imply one thing. You have to have that charge.
Can we imply the non-bonding electrons?
And then that falls into rule 4. The non-bonding electrons are very often implied. They're only implied to your nitrogen, oxygen, and halogens. They'll never be implied to carbon. Nah, that's not true. Okay? If we had that structure, that's now wrong because that carbon is negatively charged, and we can't imply the negative charge. However, you will sometimes see this. Now we are implying the lone pair because the only way carbon can be negative is if it has that extra lone pair. Okay? That's kind of a rare part. For the most part, your lone pairs are really only implied off of nitrogen, oxygen, and halogens. It's very rare to get a negative carbon, which is why we tend to not see that lone pair issue pop up as frequently. As kind of a side note, why is it rare to get carbon to be negative? Nitrogen, oxygen, fluorine. What can you tell me about those 3? The most electronegative elements. And by being most electronegative, what do? Pull all the electrons towards them, becoming negative. So finding oxygen, nitrogen, or a halogen as a negative charge is pretty standard because they're electronegative. What about carbon? Not so electronegative. What does that mean? It's not easy for it to get a negative charge. Can it happen? Yes, but it is exceedingly rare. Okay. It's actually so rare that we have to name the reaction over the person that discovered it under most circumstances. Okay. So those are big simplifications. All of those not necessarily fall out of Lewis structures, but you could then apply to the Lewis structures that you've been drawing. Okay? Kind of make sense? Okay. So now that we've got our basics down there, what we'll do is scale upwards into our functionality. Okay, and what we've got here is a chart of electronegativities. Okay. Again, you don't have to have them memorized, but knowing roughly what they are relative to each other can help you out. Okay. Remember, when we're running all chemistry, we're striving for neutrality. We're trying to neutralize those reactive species. The reactive species would be the things that are not neutral. So anything positively charged and anything negatively charged. Okay? The species that are shifting out of neutrality, not, well, yeah, that works for what things, would be the ones that are very electronegative and those that are very not electronegative. Okay? Those are going to be our kind of our reactive atoms. So we want to keep our focus around them because those are going to be our primary concern. Okay? So what happens when we start linking atoms with each other? Okay. Well, if we take a hydrogen and attach it via what's known as a sigma bond, which unfortunately is in our hybridization video, right, or a single bond to a carbon, nitrogen, oxygen, or chlorine, we end up with different reactivities. Why would we end up with different reactivities when I attach hydrogen out to those elements? What is different about carbon, nitrogen, oxygen, and chlorine? Electronegativity. So by changing the electronegativity of one of our atoms, we change the chemistry. Well, if we change the chemistry, I want to be able to classify it instead of always referring to it based off of that chemistry. That's where we come up with our functional group names. Okay? And in this case, what we're almost looking at in all of these is trying to reference kind of a substituent. So we'll see the YL ending show up. What else is changing as we go from carbon, nitrogen, oxygen, chlorine? Size. Where's the size difference pop up? Is there a difference between carbon and nitrogen? It's one of those questionable ones. A little bit, I'll accept that one. That nice kind of half ground. Okay. Officially, yes, but within organic chemistry, that size differential between those is virtually negligible, so we can ignore a size difference within a row. Where do we see size contribute? Chlorine is no longer in the same row as carbon, nitrogen, and oxygen. There's our size differential, which is one of the reasons why its chemistry changes significantly from the other ones. Okay? Even though the electronegativity isn't as high as, say, oxygen and nitrogen. Okay? So by linking these things, we can end up with different functional groups. We have the alkyl, which we could refer to as alkanes. We have amines. We have hydroxys, which I personally hate as a reference, but in this system, we don't have a better way to name it. HCl ends up being our acid. If we move down to now carbon instead of hydrogen being the one connected. If we connect carbon to carbon, we've got alkanes, carbon to nitrogen, amines. Notice the amine shows up in two different places. Okay? That chemistry can get a bit ambiguous when we refer to a structure by the amine name. Because we could be referring to a carbon nitrogen, we could be referring to a hydrogen nitrogen. And yes, that makes a significant difference in the chemistry. Alkoxys, halos. Okay, so these are the kind of names that pop up that you'll be seeing periodically throughout the semester. What happens if we move from being a sigma or single bond up to a multiple bond, like double or triple? Okay. That's where we're bringing in pi bonds. And in this case, I'm not specifying how many pi bonds, which you may remember as a term from Gen Chem. Carbon to carbon, that's where we get alkenes and alkynes. Carbon to nitrogen, imines, okay, or nitriles. Carbon to oxygen, carbonyls. Okay, so it's looking at the sub-pieces of our larger functional group systems. Okay, and all of those change just based off of what element we're adding to it because size and electronegativity change. Okay? The different names are really just coming back to, well, I have different chemistry. If I have different chemistry, I want to be able to name those functional groups so that I can identify them quickly. Okay? There's a fun part. What happens if I combine several of these? Okay, so let's do a quick test on how well you guys have been memorizing your functional groups. So I told you to start that. Let's take OH. How would you name that one?
Hydroxyl.
Okay, a hydroxyl, okay. If I had a carbon there? alcohol. Okay? Hydroxyl is generic. I don't know what that OH is attached to. As soon as I put a carbon there, now I might start to be able to say that it's an alcohol. That's one of those ones I didn't quite tell you to memorize yet. It's a carboxylic acid. Okay. How did we change? We started with hydroxy, and we added a single sigma bond. Really didn't seem to do much. And we now called it an alcohol. Okay. We've changed the functionality just by adding an atom. That's pretty silly. Okay. We changed that further by adding a second functional group. There's our carbonyl. If we have the carbonyl immediately attached to an alcohol, it becomes a carboxylic acid. Did that change the chemistry significantly? Okay. We drink alcohol, we tend to avoid drinking acids. That's probably a pretty significant difference in chemistry. Okay? So it's recognizing that when we combine these things in different ratios, we end up with different functional groups because they will all have effects on each other. Okay? It's not as simple as just 1 to 1. It's 1 to 1 to 2 to 3 to 4. Okay? And that's just looking at how these things are connected. Okay? So there's our functional group list. Again, keep working on this, trying to get those functional groups nailed down and memorized. Okay? I'll address one thing just because I saw somebody working on this in class or in the tutoring center. We just said the carbon-oxygen double bond was called a carbonyl. Where does it say carbonyl up on that list? Where does it say carbonyl? I don't want double bond. Where does it show carbonyl? Where does it say the word carbonyl? Maybe it says it down there. It's not on there. Interesting. Why is it not on there?
Where?
Does somebody see a carbon-oxygen double bond up there? Yeah, multiple times. Why do we not just reference the carbonyl? There are 2 missing bonds to that carbon. Depending on what I attach those to, the chemistry goes from relatively benign ketone to super reactive carboxylic acid. Okay? So the carbonyl as a functional group really isn't a functional group, it's a functional group piece. So yes, you should be able to know that's a carbonyl, okay? But focus more on the larger functional group. So what is the difference between the carbonyl and, say, the ketone? The carbonyl we've got shown in red. What is the difference between the carbonyl and the ketone? The carbonyl in a ketone is bonded out to 2 carbons. Okay? Do I have to specify those 2 carbons? Yes. If I don't specify them, it could have been an aldehyde. It could have been a carboxylic acid. So when you're looking for identifying your functional group, you have to identify all of the atoms that define it as that functional group. Okay? Which SmartWork is picky on. Okay? Partly because you need to be able to acknowledge these differences. Make sense? Okay. So now into our actual forces. Reaction versus interaction. I believe in the video, well, actually, let's try it this way. Anybody have any questions about what the video showed for these, right? Because didn't we have like Cl, Na, Na, Cl, and said which of those interactions was our primary? Everybody, for the most part, got those all right? Like that was easy. That was easy. Why are you asking me this kind of stuff? Except for maybe down here. Am I right?
Yeah.
Which interaction is stronger? Just looking at the bottom. We got top or, oh, I see what you're saying by third. Never mind. So let's redraw the sodium chloride one real quickly. Which interaction was stronger for the sodium chloride? Careful, I didn't draw it the same. That was an accident. The bottom one ends up being the stronger of those 2 because we can go through and apply charges. We get negative to positive in that bottom interaction. That negative to positive means a strong attractive force to neutralize that charge. That's why that attraction is there. So we get a very strong interaction from that ionic compound with sodium chloride. That bottom one is by far the stronger of those two. But if we look at the CH, we now again have two options. We'll call them A and B.
Wait, I have a question. For the first one, you said the bottom reaction was stronger?
So remember, it does not tie to the video because I think the video I've got them swapped.
Yeah, you did. Okay.
Yeah, that's why I drew it out. And we said we have to evaluate the difference in charge. Because this is another big thing. You might say, well, you said top before.
Oh, okay, I see what
Okay, where are my shoes? Actually, here, let's pause the video for a second.
Okay.
So when we're doing these
How did we establish those charges? Anyone else want to jump in? How did we establish those charges? It's not metal and non-metal. It's electronegativity. Do we have to look at electronegativity to predict our forces? Absolutely. Okay. That's how we decide those forces, that the sodium is positive and the chloride is negative. If I move to a new sodium chloride, what's going to happen there? Sodium is positive, chloride is negative. Go ahead.
So does it mean
It is pulling electrons away from the sodium. Yes. That's why the chloride becomes negative and the sodium becomes positive. Exactly. We didn't say anything about the bond. What we're then talking about is the force. Okay? Which force do I want to match up? So remember, everything we do, neutral. Everything. So let's look at the top interaction. What is the overall charge in that interaction? -2. Is that neutral? No. So that's not very good, but maybe it's the best we got. What is the overall charge now here? Which is the better interaction? Our green one is the better interaction because it neutralizes those charges. We establish those charges through electronegativity, distance, or us envisioning how those molecules then get near each other allows us to evaluate the strength of the attraction between them. Once we do that, then what do we have to do down below? We do the exact same thing. Okay? When we did the positive negative up here, okay, that was going off of big trends that we had memorized, that metals tend to be positive. Why do they tend to be positive? I do not accept the charge. What? They are the least electronegative elements on the periodic table, which then means they give up their electrons to the chlorine. That's how we get that charge. What happens when we move to carbon hydrogen? What's that?
We just determined which one is more.
Okay. So I like that idea. Let's look at electronegativity. How many of you memorize the electronegativities? Okay, so I like where you're going with that, but it didn't work for us. Do we have a rule of thumb that we can apply back to our bonding natures? The answer is yes. The carbon to hydrogen bond is non-polar covalent. It is non-polar covalent because what is the difference in electronegativity? So small that we ignore it. If there is no difference in electronegativity, what charge builds on that carbon? 0. What charge builds on the hydrogen? What charge builds on the other carbon? What kind of interaction am I going to get? Which of those is more neutral? A or B? They're equal. 0 and 0 is the same as 0 and 0. There is no difference. So which interaction? That's where the quiz was a jerk.
Oh, so the third interaction.
The third interaction that was never directly asked.
Damn it.
Sometimes we have to branch outside of our understanding within multiple choices and say, neither of those answers was good. Is there a better one? Okay. Welcome to organic chemistry. Okay. We don't get a good interaction, which means, what kind of interaction would we get? If there's none, then we'd say an incredibly weak one. That's where we run into van der Waals. It's so weak that we actually ignored it until van der Waals came along and said, actually, you can measure that. Okay. Thank you, van der Waals. Because now what do we have? A new intermolecular force that we then have to manipulate and understand and see how it works. Okay. Can we use this to our advantage? Which would we predict to be more reactive, a carbon-hydrogen bond or a sodium-chlorine bond? Sodium-chlorine, because it's charged. It's already generating a stronger interaction than the interaction we're getting between carbon-hydrogen molecules. So understanding something about the force and the strength of that force gets us to reactivity. Okay? If we don't look at the forces, what are we doing? We are memorizing everything. Okay? That's a long, probably 200 days that you're going to have to memorize. Okay? That's ballpark 2 semesters. Okay? Yeah, stepwise through all that. So that then gets us to our intra and intermolecular forces. Intra is within the molecule. This is our standard bonding. This was ionic, polar covalent, covalent. Okay? How do we know we have a polar covalent bond? What's everything else?
Everything else that isn't ionic.
That's the better definition at this point, because I haven't defined what ionic or covalent on. Our polar covalent is anything that is not ionic or covalent. Okay? Which is everything else if we've defined those other two. Okay, how about our forces? How do we know what our forces are? When do we see, say, a London dispersion force? Also known as van der Waals. Only when we have very small differences in electronegativity that are often generated by covalent bonds. Okay? When do we see a dipole-dipole force? When we have molecules that generate some kind of charge. Okay? That makes them attract to each other. That charge is not permanent. It is not an ionic charge. It is a polar covalent or partial charge. So our dipole-dipole force comes directly from our polar covalent type bonds. When do we see an electrostatic force? Only when we have an ionic bond. So by understanding our bonding nature, we can then define the forces. Okay? You'll notice I did not label hydrogen bonding. When do we have hydrogen bonding? Okay, we have to have a hydrogen-bound oxygen, nitrogen or fluorine. And one really, really important rule. Whoops, that's an eraser. Must have must have hydrogen is not a bad one, except rule 2 has our hydrogen in it, so I don't quite accept that. How do we generate polarity? What type of force is coming out of polarity? You must have a dipole-dipole. So when you're trying to identify forces, I narrow it down to 3. We have London dispersion, dipole-dipole, and electrostatic. Directly one-for-one match to our intramolecular bonds. Hydrogen bonding is a special case of dipole-dipole. So if I've generated a dipole-dipole, then I can have hydrogen bonding. Okay. What's that? How do I generate a dipole-dipole bond? From a polar covalent bond. So yes, I will need polar covalent bonds. Okay? Kind of makes sense?
Isn't the first one implied by the second one?
Sometimes, depending on how well you apply those rules, yes. So focus on the dipole-dipole first, and then you can look at your hydrogen bonding. Okay? If we put it all together, really what we're looking at in all of chemistry is a spectrum of interactions. No interaction to a really strong interaction. Right? Which is really starting at London dispersion. My pen works. No interaction that slowly scales upward in strength until what happens? It starts becoming a bond. That interaction becomes so strong that it becomes a non-polar covalent bond. Okay? We have arbitrarily split that in roughly half. On one side, we say, well, they aren't really bonds yet. And on the other side, we're saying they are bonds. So that's bonds versus forces. That's intra versus inter. Okay? What happens when we compare those molecules or pick atoms from different molecules and have them interact with each other? Well, we're looking at how the bonds apply back to the forces. So if I have a green polar covalent bond, what kind of force would I expect? A green dipole-dipole force. That's the whole point of the color wheel. It's a 1-for-1 match across this. Okay? And this usually gets misinterpreted fairly heavily. Sodium chloride versus methane. Those actually visible? Close enough. Which has the stronger bond? Why does sodium chloride have the stronger bond? What about it are you saying just because of the picture? Because the picture certainly doesn't say that. Why are you saying sodium chloride is a stronger bond? What is the phase of sodium chloride? What is the phase of methane? Gas. Do those phases translate back to their bond to nature? Yes. So which one would you expect to have the higher melting point? Sodium chloride, why? Well, you have energy to break the bonds in methane too. Okay, there's our connection. There's the misperception. What is breaking when we shift our melting point or our boiling points? The intermolecular force. So when I look at methane's intermolecular force, what is it? London dispersion. Whoops. And I look at sodium chloride's intermolecular force. What is it? Ionic or electrostatic. I'm going to go with ionic because it has fewer letters. Which of those is a stronger force? Ionic. So we would predict ionic's melting point to be higher based off of the force. That was not the question I asked at the beginning. What was the question I asked? Which one has the stronger bond? When I melt sodium chloride, what's breaking? It's breaking the forces, but in sodium chloride, what is the difference between the force and the bond? Not much. So it's really breaking apart everything in sodium chloride. When I melt or boil methane, what is breaking? The force. What is happening to the bond? Staying there. Did the bond break? Did the bond break in sodium chloride?
Yes.
Which bond is stronger? Methane. Okay. We are applying our intermolecular force understanding with phases and saying that's now the bond. That is not a bond. That is an intermolecular force. The stronger bond is actually in methane, which is why when we heat up methane, what happens to the bond? Nothing. What happens to the bond in sodium chloride? That starts to break. Okay? We didn't bring combustion into it. That's a reaction, not heat. So this is what explains your melting points and boiling points. It's the intermolecular force. How do we determine the intermolecular force? Look at the structure, identify your bond, tie that back to a force. The stronger the force, what happens to the melting point or boiling point? It goes up because I need more energy to rip those molecules away from each other. Not atoms, molecules. Right? What happens when I move to solubility? Right? Well, when I'm looking at something dissolve, what's happening? I have two things. What are those two things? A solute and solvent. To get those two things to mix, what do I have to break? The forces between what? Break all of the forces within the solute, break all of the forces within the solvent, and then somehow mix them where they now, both of them interact. So I'm looking at a balance between those. Okay? If I start with really strong forces in the solute, what am I going to need to make in the solution? Really strong forces. Because if I don't have those really strong forces, why would I break apart the solute? Wouldn't. Okay? So it's a balance between breaking the forces within the solvent and the solute and then making new ones. The only way this really works evenly is I'm looking at the same force in both systems. So water will mix really well with any kind of hydrogen bonding solvent. Okay? Because similar forces. Okay? If we move to vapor pressure is more of a Gen Chem one. That's kind of a fun one to break down. If you really care, you can talk to me after class. But I don't really want to talk about it now. This also goes into reactivity. Okay? By generating these large charges in the polar or in your bonding side, that makes stronger forces. If the forces become strong enough, what happens? If someone pulls hard enough on my arm, what happens? It breaks off. Okay? If the force is strong enough between molecules, it can cause bonds to break. That breaking of a bond then generates new molecules. Okay? And then theoretically, cyborg me when I put a new arm on. Okay? This is all going back to those forces or those sections within your chapter. You should read through them carefully. Okay? So let's take a look at some of the repercussions. Melting point, it's the energy necessary to cause a phase change. What is resisting that phase change? The forces. Identify your forces, you'll be okay. So we could compare methane to water. Come on, pen. We've got methane and we have water. Which one's going to have a higher melting point? Why? It has hydrogen bonding. Hydrogen bonding is a stronger force in water than the London dispersion forces or van der Waals, however you want to phrase them, in methane. Okay? So what species are going to have higher melting points and boiling points? Ones with stronger forces, like hydrogen bonding, okay? Like ionic. Okay? Why will we typically not see ionic that much? Ionic bonds involve what two species? Metals and nonmetals. When we looked at the periodic table that we abbreviated, how many metals were on it? Not too many. We don't see ionic bonds that frequently in OChem. Okay, how about solubility? This is the ability of two substances to mix officially homogeneously. What's going to help this? Similar forces. What hurts it? Dissimilar forces or different forces. Okay? I was going to drop structures on that. Our general rule of thumb is that like dissolves like. I would append some extra words. Like forces dissolves like forces. Okay? Is that going to be as simple as that? No. Okay? But it's easy enough to test and retry to come up with a new system. Okay? So let's take a look Yeah, let's just do this. I thought there was something else. We've got some new solvent terminology that comes out of this. Okay? You guys are probably used to these two terms, and I personally hate them. That's probably because I spent 5 years looking at these two terms and seeing how nonsensical they were, and you haven't yet. Okay? Polar and nonpolar are horrible terms. They're way too vague to be applied to really anything, because you can devise a system where someone says a solvent is polar and change how you define polarity, and all of a sudden that solvent is nonpolar. Okay? So stop with polar and nonpolar and think more back to the forces. Okay? We can still kind of apply it. So let's look at forces. What forces would you think would be easier to apply to our polar versus nonpolar? Dipole would be what? Polar. Okay, and again, lazy. Is DD okay? Okay. What forces would be nonpolar?
Covalent. Oh, sorry.
What is covalent? No, you open the can. What is covalent? Covalent, yes, is non-metal, but so is polar covalent. I still don't accept that.
Something bound to itself.
What is covalent? It's a bond, and when we're looking at solvents, we're looking at things that are using forces. So, no bonds. So our nonpolar would be our force generated from our covalent bond, which would be London dispersion forces. Are there other forces that we could stack in here? Hydrogen bonding. So what we're going to do is further refine our polar, because I can have a dipole-dipole solvent and I can have a hydrogen bonding solvent, and they are drastically different as far as their polarity goes. Water is a good hydrogen bonding solvent. Dichloromethane, those are CLs, is not a good hydrogen bonding solvent. The bonds in water are polar covalent, which gets us our hydrogen bonding in dipole-dipole. How about the bonds in dichloromethane? Carbon-chlorine is polar covalent, which would generate which force? Dipole-dipole, which puts us in the polar category. Okay? We got back to it. You're okay. Would those be expected to have the same solubility? Those of us in lab, these are both polar solvents. Do they mix? They did not. So our differentiation between polar and nonpolar does not work very well for us, because we have two solvents here that both fit as polar and they don't mix with each other. Okay? The why becomes trickier. We'll leave that to people in the lab. Okay, so we need to add an extra category. What's that extra category we bring in? Two extra words, protic versus aprotic. What does protic mean? What does prot sound like? Proton. What do we use proton word? I was hoping you just accepted it and said something. But that worked. Hydrogen. Yeah, it doesn't have to make sense if you get the answer right. Hydrogen. Proton is our abbreviation for a hydrogen. So if we have a protic solvent, what would we expect to see in our molecule? Hydrogen. Okay, so a protic solvent would be like dichloromethane? No, when we're referencing that protic of hydrogen, what are we instead referencing? Hydrogen bonding. Water is our example. It is by definition a polar solvent. Okay? So we could say it is a polar protic solvent, or we could just say protic. As soon as we say protic, the polar is implied. Okay? What does aprotic mean? It does not mean not polar. It means not proton, which is then also referring to not hydrogen bonding. What is the case of dichloromethane? It is aprotic. Is it polar? Yes. So we have multiple classifications that can come out of this. We have polar protic. we have polar aprotic, we have nonpolar aprotic, and we have nonpolar protic. What's the what? Yes, I agree.
I just got really confused.
You lost track of all of them. Let's run them through again.
I was about to draw some bunch of arrows.
Hey, you might want to hold off on that. Polar protic, polar aprotic. Nonpolar aprotic, nonpolar protic.
So what about for non-polar?
We draw on some lines. We got these two. We got these two. And then we've got, that's a big long line, these two and these two. So 4 possible combinations. False. Good answer. What's the false? Nonpolar protic. That cannot possibly be an answer because protic, by definition, is polar. Okay? So our nonpolar protic does not exist. We really only have 3 solvent classifications. Polar protic, polar aprotic, and nonpolar aprotic. Okay? Of those 3, we can also whittle those names down, because I'm sure you guys loved hearing all those listed off. So let's do it again. One of those solvents, we can call it just protic. Why do we ignore polar? Protic, by definition, is polar. Polar aprotic. I'm going to have to keep that one, because polar could be aprotic or protic. Okay? And then nonpolar. Do I have to specify aprotic for the nonpolar? Nope. By definition, it will be aprotic. 3 solvent classes that we want to manipulate and use. Which brings us to the next fun little bit. So let's apply this. So let's start with the first part. If we look at our solutions, or look at those reactions, we're trying to pick a solvent that will allow them to work. Okay? For a reaction to work, what has to happen? They need to interact, which means what?
They need to be shared.
Easier. That's going to come into play in a second. All we're talking about is those 2 molecules. Okay, molecule A and molecule B. For them to interact, what has to happen? Right? We've got valence electrons that have to share. Yeah, I agree with that. They need to come in contact with each other. How do they come in contact with each other? They're in the same phase. How many of you can interact with the people outside this room? Okay. It becomes a little bit more difficult to interact because there's a barrier in between. So when we're running a reaction, what do we need to do? Remove that barrier. Okay? So they must all get into the same phase. So if we take a look at that first reaction, or that first thing, we got 2 species. Which one did you focus on first? Okay. I would argue you should focus on this one first. Why should you focus that one first?
Because it needs to be neutral.
It's charged. It's going to inherently be the most difficult one to deal with because it's the most reactive. Which solvent do I want to dissolve a charged species? Polar or nonpolar?
Polar.
Polar. Nonpolar won't work. It's wrong. All right. Now we have our next choice, protic or aprotic. Okay. If we go aprotic, okay, we're just saying there's no hydrogen bonding. Well, what happens if we add hydrogen bonding? Hydrogen bonding brings in what structure? Protic. Why do we call it proton? It's positively charged. That's why we call it proton, right? Proton is a positively charged species. If we bring in a positively charged species, what is that positively charged species going to do? It's going to neutralize that negative charge. If that negative charge is neutralized, can the reaction go? Ooh. If I add that positive charge, the chloride disappears. If I don't have a chloride, can I do the reaction? Nope. Is a protic solvent a good choice? Nope. What do we want for that top one? We want polar aprotic. These are big leaps, okay? But this is what we're doing. Bottom one. What happens in the bottom one? What do you think? Polar or nonpolar? Polar, why are you saying polar? There's a couple reasons to jump on the polar train. We're starting with a charged chloride here, though this one's a bit misleading. Did that chloride do anything? If we look at the products, it did absolutely nothing. So looking at the chloride doesn't necessarily help us. Okay? Unless we're looking at the wrong product. What are the other products produced? 2 charged species. For us to form charged species, are charged species high energy, low energy? High energy, which means for that reaction to go, I need to make those charged species as stable as possible. How can I make them stable? By bringing in some kind of polar thing to neutralize those charges. So polar works again. Okay. Do I want it to be protic or aprotic? I need to stabilize those charged species as much as possible. Which solvent does that? The protic. And I want the polar protic solvent for the bottom. Okay. Is that the way it actually works? Yeah. Yeah, it does. All we do is just play with some forces and solubilities, and we can predict how a reaction is going to work and what solvent's going to allow a reaction to work better than another. That's pretty phenomenally cool. Okay. Let's move to the next one. Melting points. Okay. How do we decide melting points? Intermolecular forces. So we need to find the highest intermolecular force. Okay. This becomes a bit tricky, kind of unintentionally. Why has it become tricky? We have a positive charge on number 4, and you say, well, I don't have a metal, so I don't have an ion. Wait a second. What is a positive charge? A cation ion, which means number 4 has an ion, which means we're looking at ionic forces. 4 will likely be the highest. What will be the lowest? 1. So we got 4. Lowest is 1. Then I've got 2 and 3. Between 2 and 3, what are our forces? 2 is hydrogen bonding. 3 is dipole-dipole. Melting points you should have been able to nail down. Liquids, what happens? C is the highest. That has hydrogen bonding, I agree, but doesn't B?
Yeah, but C has a polar chloride or dipole-dipole, whereas B just has...
B and C both have hydrogen bonding. C has an extra, if you will, dipole-dipole interaction, which puts C above B. Then what do we have? A and D. Melting points. These are things you guys should be able to nail down because this is not the first time you've seen it. Right? It's shown up if you went all the way back to 130. It's shown up in 130 and 151. I don't think it really showed up in 152. I know, that could have been a long time ago. But you've, in theory, already seen those. Let's take a look at our solubilities. We want to match the best forces we can. I would argue one of these is the easiest. 1D should be the easiest.
What if we didn't have enough time to write?
They're both non-polar, London dispersion. That's going to be our best bet. Okay, after that, what do we have? 2C. Okay, why are you picking that? Both have hydrogen bonding, so that's not a bad guess. Doesn't B also have hydrogen bonding? Yeah, so we probably could have done that. Okay, what else could we have done? 3 then. Probably best matches with A. And 4. Kind of sucks, but the best one for 4 is probably C. Okay. It's the most polar solvent we've got. We just didn't really have anything more polar.
But they probably wouldn't interact with each other.
Yeah, probably minimally. Okay. Kind of makes sense. So you're applying forces, you're making those comparisons, you're trying to set it up. Let me just check here. We'll look at application of these forces with our interactions. Unfortunately, I can't answer any questions today because we're done, but you can ask after class. We'll look at how we apply those interactions out into soap and making ourselves clean, and then Wednesday, we'll look at bonding.